Section 10.4 is called equivalent circuit of a practical transformer. So let's take the things that we've learned and let's sort of put this together, and then we're going to end up with an actual table of some of these values that we can compare transformers from, and look at that and sort of see some usefulness of some of this tough stuff that we've endured here for the last few sections. So let's look at, let's go back to figure 10.7. And what we can see from figure 10.7 is that it's composed of resistive and inductive elements. We've got, in terms of resistive elements, we've got R1, we've got R2, primary, secondary, we've got XF1 here, and we've got XF2 here, and then we've got a load coupled out here, connected out here, and all of this together is coupled by this mutual flux that we indicate from here. All right, and this links the primary and the secondary windings across there. So the leakage-free magnetic couplings enclosed in the dotted square, which we talk about in terms of being this ideal transformer, right? So inside the square is all that stuff that we looked into when we were talking about the ideal transformer. So I've got this cool iPad and I'm going to use it, and so that would be everything in there. All right. So when you think about this in those terms, this is chapter 9, and chapter 10 adds all these additional elements across there. Okay. So this ideal transformer, it possesses same properties and same rules that we looked at. For example, we talked about shifting impedances, where you to the primary side, and we can multiply, their values and shift, by this, N1 over N2 squared term, and going through that shifting exercise that we went through, or A squared, it was the other way that we looked at that. So if we take this a little bit further, so we've got all of this, right? And we understand where all these things come from. Now, if we add X of M and we add R sub M, and that represents a practical core in terms of, heat losses and, saturation considerations. And then when we add those to also this practical, this ideal transformer here, we add that to that. Then what we've done, and he mentions that the T is the ideal transformer part of this. Then what we've done, and we recognize that terminals 1, 2, 3, and 4 are all that we have to access, and that all these components, everything in here is going on, but it's buried, right? And we just need to know the characteristics of that. And then, once we know the characteristics of that, this is all we can do, right? We can connect a voltage source on the primary side, and we can connect a load on the secondary side. So, that's all we can do in terms of, modeling this thing. All right, and this is all we have accessible. So let's look at, actually it's a table 10A, and I think I can pull that up here. So, here is table 10A. And he tells us that typical values of these of things that we've been looking at, for instance, let me go to highlighter here. Here's typical values for R1, that resistance that we saw on the primary side. Here's R2, right? And here's XF1 and XF2. All of those values are there. And let's see, what else do we have? We have X of M, R sub M, all these, things that we've looked at, you know, in these various models are actually accessible in information about transformers. And it's, you know, things that we have to consider in terms of specifying a particular transformer, or maybe there's an application where we're troubleshooting, or maybe it's more of a, you know, we're having to replace, and, you know, maybe the one that was originally installed is not available anymore, so we have to, you know, match it up as best we can. So notice that the values for the transformers, they range in terms of that doesn't work very well. They range in value from 1 kVA all the way, and when we talk about power systems, this is the world we play in, all the way up to 400 megavolt amps, or 400,000 kVA. Huge transformers, right? You know, where you're looking at, look at the currents, primary currents that are, you know, look at these numbers, you know, and this is real world stuff. This is what's out there in the power world, and the thing that we have to consider when we walk through it. We've got nominal voltages, right? These are the voltages that you know, these devices can be connected to, and the range there, we see the primary secondary currents range from, look at this, 0.417 amps all the way to 29,000 amps. The excitation current is given here, okay? The I sub O for the various transformers, it's always much smaller than the rated current, right? We see that. And note that in each case, this is always going to hold true. ENP times INP will equal ENS times INS, okay? Because the power in equals the power out. Of course, there's losses in between there, but, you know, so basically, you know, if we looked at, you know, any one of these values, we could plug values in here, and we could see that that would indeed be the case for us. I mean, we can walk through one, you know. I know you believe everything I say, but anyway, so if I choose the first one, EMP is 2400 and IMP is 0.417, okay? We're saying that ENS on the secondary side, 460, times INS, 2.17, we're saying that that's going to be equal to each other. You know, and that's the characteristic of the transformer, right? The power stays the same, the voltage times the current stays the same. What changes is the combination, the breakdown between the voltage and the current. So I went ahead and quickly did this for you. Now notice this. Notice that it doesn't come out exactly equal, does it? So, you know, there was power in that we don't see on the power outside. Now we're going to talk about where that comes from. That's not just a rounding thing that we're looking at, but you know, it accounts for some losses in that conversion from primary to secondary. Okay, well that knocks out 10-4. But before I leave that, you know, basically, you know, this is, if we were looking at ideal, you know, we're saying those are equal. I mean, you know, so they're so close, you know, they're equal. So in general, we say the power in is equal to the power out, although there are some minor losses. Okay, that's it for 10-4.